Japan has constructed a barrier so vast that most people worldwide remain unaware of its existence. It rises higher than a 4-story structure. It stretches 400 kilometers. Its total cost reached $12 billion. That distance equals driving from New York to Boston and returning twice. Every section is built with meticulous care. Construction began after 2011. This is its current state. The barrier stands because of events on that fateful day. The wall reaches such height that ocean views from homes have vanished in many areas. One resident described her husband running toward the sea, never to return. Each segment carries stories of loss. Engineers caution that failure could worsen future waves. March 11, 2011, the seafloor shifted 50 meters within 3 minutes. What followed proved overwhelming. That movement displaced 500 kilometers of ocean. The resulting surge reached Japan in 30 minutes. Not merely a wave, but an advancing front of dark water up to 40 meters high. Little in its path endured. 90% of existing coastal defenses collapsed during that hour. Every Japanese engineer took note. The world's largest breakwater, valued at $1.6 billion, vanished in moments. It failed not from direct impact, but from water overtopping and eroding the rear. Its foundation disappeared. That revealed the core challenge. One community, one protective structure, saved 3,000 lives. That town provided Japan's model. Build higher. How does one design something to withstand an ocean's force? The honest reality is this wall was never meant to stop the exact 2011 event. Most of it remains hidden below ground. Only 14 meters appear above. Engineers simulated this barrier 200 times digitally before placing any material along the coast. Height varies by location. Taller along exposed points, shorter in protected bays, determined through wave analysis. 440 separate teams participated. Failure of any could create vulnerabilities. Zero tolerance applied. Survey vessels examined seabeds thoroughly. Every portion differs underground. 3 foundation approaches addressed soft clay, dense sand, and solid rock. Each demanded unique solutions below the surface. Initial work involved removing failed defenses. Every collapse mode received study. Then, reconstruction began larger. 400 kilometers measured precisely before machinery started excavation. This phase required months. They removed an entire coastal pine forest. Erosion control followed bulldozers immediately. Tides limited work to 4 hours daily on the seabed. Every moment counted. Clay areas could not support heavy equipment. The ground proved too unstable. Steel plates distributed weight. Machines essentially floated above the mud. Simple yet effective. Crisis resolved. They constructed foundations 25 meters below sea level in active surf. Divers positioned 5-ton boulders underwater in the same waters that previously devastated the area. Engineers monitored progress through sonar. Visibility remained impossible. They relied entirely on data. Between boulders and fill, a filter layer prevented soil migration. Missing it would cause gradual erosion. After weeks submerged, the rubble mound emerged. What followed was critical. That geotextile membrane stopped fine particles from washing into the rubble. It functions continuously. An uncompacted mound settles irregularly. A shifting foundation would tilt the structure. Every roller pass prevented failure. A 1-to-5 slope ratio proved exact. Steeper risked sliding. Flatter reduced wave-breaking effectiveness. A platform emerged from the ocean. Now the visible wall construction advanced. Sheet piles drove 10 meters into the seabed to protect the toe. Z-profile interlocks transferred shear forces between piles. That connection proved essential. The steel faced retreating waves, not incoming ones. Backwash erosion destroyed previous foundations. One buried boulder deflected a 12-meter pile. Alignment suffered. Pre-drilling cleared the obstacle. The pile then advanced cleanly. Retreating water proved more destructive than advancing surges. Backwash vacuum pulled foundation material outward. 30 dump trucks operated 16-hour shifts continuously. Any breakdown halted compaction. 300mm layers. No thicker. Excessive thickness prevented full compaction. Geotextile reinforcement within the embankment acted like rebar and concrete for fill material. 98% proctor density or work stopped. Every layer underwent testing. Pressing on 98% proctor fill shows no movement. At 85%, sinking occurs. 300mm daily. 18 months until the first tsunami season with the barrier standing. That clay core provided internal waterproofing. Well-compacted clay blocked water permeation. One heavy rain caused 600mm of slope failure. The section required complete rebuilding. A drainage network inside the embankment. Cover slopes with geotextile before it rains. Always, the wall reached 10 meters. Thousands of concrete panels arrived. This phase proved vital. Sensors embedded throughout monitor the structure. Engineers observe movement and settlement daily. Indefinitely, the face required perfect flatness before panel installation. Any irregularity created stress points. 3 materials served distinct purposes: gripping the seabed, sealing against water, carrying structural loads, all within one system. If one 7-ton panel cracked during molding, the week's schedule suffered. Every hairpin bar connected panels to the crown wall, missing one compromised integrity. Self-compacting concrete flowed around reinforcement. Perfect surfaces. No voids. That face needed to endure tsunami forces. Incorrect consistency caused surface defects. One flawed batch halted production. Listen to the tap. Solid sound indicates quality. Hollow tones meant crushing. Zero tolerance for defects on tsunami barriers. That panel cost $800. It still faced destruction. 7-ton panels navigated narrow coastal roads. Flagmen at every intersection. 400 kilometers to cover. The bed leveled to 5 millimeters. A bump cracked a 7-ton panel corner. That surface faces 30 km/h tsunami impacts. It must last 100 years. 400mm overlaps sound minor until imagining tsunami forces ripping panels away. That rubber water stop swells when wet. Larger waves tighten every joint automatically. Straight panels on curved coasts created 20mm gaps. Water forced through, undermining below. 37 unique panel shapes. CNC machined molds. Every gap closed completely. One curved bay sealed perfectly. 1 week covered 400 meters. But the 2022 deadline approached. 440 teams worked simultaneously. The crown wall nose deflected overtopping water seaward. One detail protected thousands. The crown wall secured every panel below through hairpin bars. One unified structure, not separate stacked elements. Pump boom reached a maximum of 15 meters. Failure mid-pour created cold joints. Structure compromised. 10 degrees from vertical. That angle threw overtopping water outward rather than inward. Simple, yet effective. The only decorative element along 400 kilometers, a stamped wave pattern on the coping. They monitored crown wall height for 5 years post-completion. Observation continues indefinitely. 6 materials. 6 distinct engineering roles. From outside, it appears plain gray. It is not. The rear proves as important as the front. Rear failure destroyed previous versions. If water overtops, it requires safe dispersal. The landward drain provided that path. 32-ton concrete blocks. Each needed interlocking or the armor layer shifted in the first storm. One leg always pointed upward, securing the next above. That connection absorbed wave energy. Placement was not precise. Blocks dropped into position. They found stability naturally. Chaos yielding order. Gaps between tetrapods were not flaws. They formed the mechanism. Water passed through. Energy dissipated. 1 liter is absorbed completely. Imagine that scaled to 50 million tons of tsunami. A formula guided this. Van der Meer equation. Input wave energy, Output minimum armor weight: 40 tetrapods daily. 400 kilometers of armor. This yard operated continuously. Below the waterline, tetrapods accumulated unseen. Sonar revealed what divers could not reach at depth. 3 lines before the main wall: rubble mound, sheet pile tow, tetrapod armor. The Tsunami expends energy first. Every section tested in wave tanks. Some outcomes were surprising. 443 gaps in the wall, each a potential vulnerability if a floodgate failed to close. Floodgate concrete measured twice standard thickness. Forces concentrated here. 70 seconds from alarm to sealed. The only window before impact. Seismic sensors trigger automatic closure. No human intervention needed. Earthquake begins. The gate closes immediately. 15mm clearance. 50 tons of steel. 40 km/h coastal winds during installation. 1.5 times design pressure. If one of 14 seals leaked, the gate failed entirely. 40 liters per minute through a 2mm gap. Under real tsunami pressure, that widened. 2mm ground off. Retest: 0 leaks. 3 hours of machining saved communities. A driver caught in the gap during alarm faces closure in 70 seconds. A 22-meter steel curtain seals the river mouth before coastal arrival. Stored open at top. Gravity closes it. Power loss. The gate descends anyway. 443 gates. 1 control room. 4 minutes 20 seconds. Japan practices this every March 11. 400 kilometers of wall. 1 monitoring screen. Every gate, sensor, alarm, the wall operates intelligently. On cliff sections, no beach exists. The wall integrates directly into rock. Bolts extend 2 meters into basalt. 50 km/h coastal winds during drilling. Wall secured to mountain. Concrete sprayed at 100 km/h bonds better than poured. The cliff becomes the wall. Tsunami strikes concrete, bonded to shortcrete, bonded to basalt. 3 materials, 1 unified face. Nothing shifts. A submerged breakwater disrupts waves 200 meters offshore before reaching the main barrier. A 60,000-ton box floating in 3-meter swells sunk to 63 meters. Observe the process. Tug loses control in 30-knot winds. That 60,000-ton box drifts 8 meters off position. The rebuilt Kamaishi breakwater exceeds the previous record. Always rebuild stronger. If this panel fails strength testing, the week's production is destroyed. 2 millimeters of carbonation. Reinforcement inside remains protected from sea air for at least 100 years. Independent inspectors can reject sections and demand removal. 440 contractors face constant pressure. Twice design load on gate frames. Engineers monitor strain gauges. It holds. 14 millimeters differential settlement across 400 kilometers in 2 years on coastal sandy ground. Exceptional. A 7.4 earthquake strikes. Sensors activate. All 443 gates close simultaneously. 0 cracks. 0 shifted tetrapods after a real 7.4 event. That performance stands extraordinary. Observe, the pump operates on the final section. 400 kilometers nearly complete. Nearly operational. A helicopter flies the full distance now. What it captures will influence engineering for generations. These staircases serve not as scenic features. They provide emergency evacuation paths based on crowdflow studies. People cycle along the top. Walk dogs. Run daily. The barrier became a public promenade.